Okay, so this is a video from section 5.5. And what we're going to look at is what's called the substitution rule. And essentially, we're going to have an integral, right? And suppose that integral is f of g of x multiplied by g prime of x dx. You want to transform it into something that's more manageable to integrate. That's the basic idea of the substitution rule. So a lot of times instructors will call it U-Substitution. Okay, that's what we're going to learn in section 5.5. And so what I'm going to do is I'm going to let u be g of x. That's the inside function. Now I'm going to calculate du. Notice how the derivative of g is present inside the integral, right? So du is g prime of x dx. And so therefore, the integral of f of g of x times g prime of x dx. I'm going to replace g of x with u. So this is going to read the integral of f of u, and then g prime of x dx gets replaced with du. And ideally speaking, f of u du is going to be a more manageable integral than what you had originally. Okay? And with that in mind, that's the essential idea. Okay? And with that in mind, we're going to look at some examples. Okay, so let's start with example 1. And the directions say to evaluate the indefinite integral. All right. So example 1. Suppose I had the following. Okay, here's a good one. The integral of ln of x to the second power divided by x dx. Now, when you look at a problem like this, on its face, it looks fairly complicated. But it turns out it's not, because what I'm going to do is I'm going to let u be this inside function here, which is natural log of x, or ln of x. So the way you start these is I'm going to let u be natural log of x. Du, so you got to calculate du. So that's going to be 1 over x dx. So I'm going to rewrite this first as the natural log of x squared times 1 over x dx. And I did that on purpose because I want you to really see what it is I'm looking at. And so now I'm going to take this integral and transform it in terms of u. And so I'm going to replace natural log of x with u, so you get u squared. 1 over x dx becomes du. And then when I evaluate, this is more manageable than the original. I hope we can agree. And so this is 1/3 u to the third plus c. But you're not done, because remember, we have to put back in terms of x. So the original integral is in terms of x. Your answer should be in terms of x. So the final answer will be 1/3 times natural log of x to the third plus c. Example 2. Suppose I give you this one. Suppose I had the integral of, okay, so we're going to do sine of t square root of 1 plus cosine t dt. So you can kind of see this looks a little complicated, right? But what I'm going to do is I'm going to let u be the inside function. The inside function is this 1 plus cosine t. Because when I look at the derivative, it's almost present inside the integral. Because du is going to be negative sine t dt. But what I need to do is figure out what sine t dt is. So I'm going to solve for it. Sine t, I hope we can agree, dt is negative 1 du. If we're off by a constant, that's okay. We can compensate for that. And so I have an expression now for sine t dt. And so this is the integral of square root of u times negative 1 du. Right? So sine t dt became negative 1 du. And I'm going to move the negative to the outside of the integral. So you have negative square root of u du. But I'm going to rewrite square root of u as u to the 1/2. And so remember that it also, can we agree that that's a much simpler integral than what we had originally? You know what I mean? And so here, this is negative 2/3 u to the 3/2 plus c. But u is 1 plus cosine t. And so the final answer should be negative 2/3 times 1 plus cosine t to the 3/2 plus c. And that's example 2. Example 3. Suppose I had the following. Suppose I had the integral of e to the negative 5r dr. So I'm going to let u be negative 5r. du is negative 5 dr. So we have an expression for negative 5r, we have an expression for dr. Now, why? Because I can solve for dr by dividing both sides by negative 5. So this is negative 1/5 du is the same as dr. And so when I go to make my substitution, I'm going to replace negative 5r with u. So I get e to the u times negative 1/5 du. And I'm going to move the negative 1/5 to the outside. And I'm going to take the integral of e to the u du. And I want to stress something. If when you get du, if you're off by a constant, that's okay. We can compensate for that because we can solve for dr. What you don't want is when you pick a u and you have a variable r present when you get du. So in other words, you don't want an r here. If you have an r there, it's bad. If you just have a constant there, that's okay. Okay, I hope that makes kind of sense. And so this is the following. So you get negative 1/5. The integral of e to the u is e to the u plus c. But remember that u is negative 5r. And so this is negative 1/5 e to the negative 5r plus c. The key to these is you have to remember to put back in terms of r. It's not enough to leave it in terms of u. Okay? And that was example 3. Example 4. Suppose I had the following. Suppose I had the integral of z squared over z to the 3rd plus 1 dz. Now, I noticed that the derivative of z cubed is 3z squared, so I'm off by a little bit. That's okay. So I'm going to let u be z to the 3rd plus 1. du is 3z squared dz. So z squared dz is equal to 1/3 du. So I have an expression for z to the third plus 1. That's just u. I have an expression now for z squared dz. So this is all substitution all the time. So I'm going to rewrite this as 1 over u. And remember that z squared dz became 1/3 du. Just like this. I'm going to pull the 1/3 out in front, and you get the integral of 1 over u du. But this is 1/3 natural log of the absolute value of u plus c. But remember that u is z cubed plus 1. So this is 1/3 natural log of z cubed plus 1 plus c. Because remember, you have to put it back in terms of the original variable, which in this case is z. It is not u. You can't leave it in terms of u. You don't want to do that. Okay? Let's do another one. We'll call this example 5. And suppose I give you this one. The integral of sine of 1 over x divided by x squared. So I look for the inside function wherever possible, and in this case, it's going to be 1 over x. So I'm going to let u be 1 over x. So du is negative 1 over x squared dx. But it's off by a negative. And so what I'm going to do is solve for 1 over x squared dx. And that's going to be negative 1 du. Now, let me rewrite it like this. Maybe that'll help us to see it. So I get sine of 1 over x times 1 over x squared dx. Because now you can see, like right here, that's my u. Right here, this is my negative 1 du. And so this is the integral of sine of u times negative 1 du. And so this is the integral of negative sine u du. So that's more manageable than the original function. I'm going to be a broken record on that. And so here you get cosine of u plus c, but u is 1 over x. So you have to write this as cosine of 1 over x plus c. That's example 5. Example 6. Well, we can come over here. They have lots of problems. So suppose I give you this one. The integral of secant squared theta times tangent cubed theta d theta. So I'm looking at this secant squared theta, and I already know that the derivative of tangent theta is secant squared theta. So that makes a pretty good u. So I'm going to let u be tangent theta. Okay? And du is secant squared theta d theta. And so this gives me the integral, okay? Now, secant squared theta d theta is my du. That's right there. Tangent cubed theta is the same as u cubed. So we get u cubed du. We're going to integrate that. And so this is 1/4 u to the 4th plus c, but u is tangent theta. And so we get 1/4 tangent to the 4th theta plus c. Example 6. Example 7. Suppose I give you this one. Suppose I give you the integral of 1 over cosine squared t times square root of 1 plus tangent t dt. This one's kind of cleverly hidden, I guess, because cosines and tangents typically don't go together, but I do know that 1 over cosine squared t is secant squared t. So I could rewrite this as the integral of secant squared t divided by square root of 1 plus tangent t dt. And then I go, oh, okay, I know the derivative of tangent, so what I'm going to do is let u be 1 plus tangent t. Then du is secant squared t dt. Now I have an expression for everything in terms of u's. Now this is 1 over the square root of u du, which is nice. And so I could write this as the integral of u to the negative 1/2 du. And so when I come over here, this is u, negative 1/2 plus 1 is 1/2, divided by 1/2 plus c. But I have to put back u. And so this is 2 times 1 plus tangent t to the 1/2 power plus c. That's example 8. If we take a look at that's example 7. If we take a look at example 8, suppose I had the integral of, let's do this one, sine of x divided by 1 plus cosine squared x dx. And if I look at that, I already know that the derivative of the cosine is negative sine. And so that makes a pretty good u. So you have to look for a u so that when you take the derivative, it's somewhere present in the integral, if that makes sense. And so I'm going to let u be cosine of x, because du is negative sine x dx. Okay, now I could solve for sine x dx and get negative 1 du. And so this is the integral of 1 over 1 plus u squared times negative 1 du. And that is more manageable, because I'm going to pull the negative 1 out in front, and this is negative 1, the integral of 1 over 1 plus u squared du, which is negative arctangent of u plus c. But I forgot, I got to find out what u is. Oh yeah, u is cosine x. And so this is negative arctangent of cosine x plus c. And we have time for one more example in this video. So we'll call this example 9. So we'll do one more. Okay, this one's good. So we're going to do x cubed square root of x squared plus 1 dx. Now, there's no immediate derivative because yes, if I take the derivative of x cubed, I get 3x squared. The problem with that is it's inside the radical, so that's not going to do me any good. So this is one where I want to give you a tool. The way I'm going to do this is I'm going to break up the x cubed into x times x squared. And the reason why I was thinking that is because I knew that if I take the derivative of x squared, I get a 2x, right? And then I'm going to multiply by the derivative of x, by the square root of x squared plus 1 dx. And then here's how this is going to work. I'm going to let u be x squared plus 1. So that's okay. Du is 2x dx, right? Now, I need an expression for x dx. So x dx is 1/2 du. Okay, well that's good. So I have an expression for x squared plus 1. I have an expression for x dx. What am I missing? Oh yeah, I'm missing x squared. But I do know that x squared is u minus 1. So that's good. So I'm going to get the integral of u minus 1 times the square root of u. And then x dx is 1/2 du. So it's 1/2 du. So I'm going to pull the half out in front. Okay. And I'm going to distribute the square root of u in. And so I'm going to get u to the 3/2 minus u to the 1/2. That's just the same as square root of u, du. So this is 1/2 of. Now, remember that 3/2 plus 1 is 5/2. So I'm going to get u to the 5/2. But if I divide by 5/2, I'm really multiplying by 2/5. And then 1/2 plus 1 is 3/2. So I get minus 2/3 u to the 3/2 plus c. Now I'm going to distribute the 1/2 in. So this is 1/5 u to the 5/2 minus 1/3 u to the 3/2 plus c. But u was x squared plus 1. Ooh, let's go back. So this is 1/5 times x squared plus 1 to the 5/2 minus 1/3 times x squared plus 1 to the 3/2 plus c. And that'll conclude this video for section 5.5. We did 9 examples on U-substitution. And thank you.